Hello, everyone. Welcome back. So today we have lecture 14, and this is a continuation from what we talked about last class, which is confidence intervals. But today we're going to look at confidence intervals for population mean. So the same idea is going to take place where we're taking a sample and we're trying to see what's going on with the population overall. So, but now we're just working with numerical data. So we have a little bit of a different situation, but we're going to try to handle it the same way. So let's take a look at the typed notes and we'll walk through this a little bit. So let me pull these up here. Okay, so I just want to start off with just some notation. So mu, which is the Greek letter there, that is my population mean, right? So it's nothing new for us. X bar is my sample mean. Then I have sigma, my population standard deviation, and S, the sample standard deviation, and of course N is my sample size. So if we're going to look at the same calculation that we had before last class for the proportions, my calculation is always point estimate plus or minus margin of error. It's always the same calculation. So if we move on to stat 2, you're going to see that all the time. It's just now what I use in the calculation changes. So here my point estimate is my best estimate for mu, which is my sample mean, X bar, okay? And I'm going to add and subtract my critical value or my Z value right there from my Z curve like we did last class. That's based on my confidence level. And then my standard error. So now my standard error is a little different, right? Because I'm looking at numerical data. So that is my standard deviation divided by the square root of n. So I just want you to look at this. When we're calculating the standard error here, and I have it highlighted in yellow, we have sigma. So sigma is there, and that's my population standard deviation, but we need to realize we don't have the population standard deviation. So we need to estimate that with the sample standard deviation, which is S. So I have on the next page here, the new calculation. So you can see I'm using X bar in the first part of the formula. That is my estimate for mu. And S, which is the estimate for my standard deviation, sigma. So now I have two estimates in this calculation. And when I introduce a second estimate in my calculation, I'm creating more variability. And when I'm doing that, it works out that my interval doesn't actually work. Meaning, if I have a 95% CI and I build 95 of the 100 CIs built should give me the correct population mean. They should be included in those CIs. And what happens here is it's not true. I do not get 95 out of those 100 CIs with the population mean. And that is because I am introducing extra variability. So the curve doesn't work anymore. That Z curve does not work for my numerical data. So then I'm going to introduce a new curve. The new curve is called the student's T distribution. This new curve looks just like the normal curve, and it's centered at 0, just like the Z curve is. It's just now the curve is shorter, like it's pushed down in the middle, and then it has this extra area in the tails. So it's like the middle's pushed down, so you're kind of flattening this curve out. It's pushed down in the middle, and then in the sides I have a little bit more area. And that allows for that extra variability that's being introduced because of the second estimate of my standard deviation. The curve does change shape. So this curve depends on my confidence level, and it also depends on what we call degrees of freedom. Degrees of freedom is just n minus 1. We've already seen this when we calculate the sample standard deviation way back in, I don't know, chapter 3, I think it was. So n minus 1 is called degrees of freedom, and we subtract 1 because we have a second value that we're estimating, the standard deviation. So we can see that there. So I just want to show you this picture. And this is going to show you exactly what I was talking about, how it changes shape. So you're going to see the red curve here, that's the shortest one. It's my T curve with 10 degrees of freedom. So that means n minus 1 is 10, so it means n is 11, right? And you can see over here in the picture that the area in the tail, there's more, right? It's a little bit higher off that x-axis. Then I'm going to look at the blue curve. So it's the one in the middle. That's my T curve with 20 degrees of freedom. So that means N is 21, and you can see how it's a little bit taller in the middle, and then it has a little bit less area over here in the tails. Then the black curve, that tall one, that's my T curve with infinite degrees of freedom. So that is actually my standard normal curve. That's my Z curve that we use in the proportions, the categorical data. So you can see that the curve changes. So as my degrees of freedom increase, the curve becomes more normal. It looks more like my normal curve. Okay, so it's just nice to know. We don't have to actually know the exact look of the curve, but it's just nice to know that as n-1 increases, my curve will look more like my Z curve, my standard normal curve. Okay, so that's what's going on here. So now let's take a look at the calculation the appropriate way with my T curve. So it's still point estimate plus or minus margin of error. And I have my X bar right here, plus or minus, right? Now it's T at alpha divided by 2. Remember, the alpha divided by 2 is just saying the area in my tails divided by 2. So it's not really like a number I'm plugging in there. It's more of a location. So that just depends on the middle. Like if I'm doing a 90%, then that means my tails has 10%. So if those tails have 10%, then I'm going to divide by 2 to get 5% each side. Okay, that's all we're looking at there. And then I have my standard error on the right side of my calculation. Okay, so I can do this by hand, this calculation, or I can use my calculator. Okay, but first of all, I need to know how to find that T critical value before I can do it by hand, right? So if I'm getting my T critical value, I have two different ways to find this as well. Some of us can use our calculators, and it just depends if we have the function on our calculator. Some of us do, and some of us don't. And the other way is by using the T distribution table. Now, I will always supply the table for you. It's in the last page of this notes, the full size table. And I will always include it on an exam document for you. So if you would rather just use that and not even worry about your calculator, then that's fine. If you want to learn the calculator way, then that's fine as well, if you have that availability and that function there. So if you're looking at your calculator, you're going to look for inverse T, which is in the second distribution. All you have to know is that you need to put in the area to the left, right? Our calculator always knows area to the left and degrees of freedom, because that is what my curve, it depends on. So I just want to make a note that if you're calculating a 95% CI, the area to the left of my T value is not 95. 95 is in the middle. So it's the middle plus the area to the left on that left tail. So it's actually 0.975 that I'm going to plug in there. You're always plugging in a decimal into the calculator. Okay. If you want to use the distribution table, this is fine. Like I said, you will always have this available. So this is always a sure way to get this. This table just is based right on the center, okay, the middle. So whatever your CI is going to be, and your degrees of freedom. Now, you can't just plug in any degrees of freedom like you can on your calculator. There's set values, and those are on the left here. It says degrees of freedom, and along the top you will see the confidence level. So you're just going to match them up. So if you wanted, like, let's just look at an example here. I have 99% confidence level with a sample size of 18. Now remember, sample size is n. I need n-1. So I'm going to look at 17 for degrees of freedom. But I'm looking at 99 confidence level. So if I use my table, I'm going to look at the third one in from the right side. It says 0.99 right below 99%. And I'm going to read down to 17 here. And when I'm looking here at 1799, I get 2.898. Okay. And I will get the same value if I plug it in my calculator. So if I go into my calculator and I plug in the area to the left, which is 0.995, right? It's not just the 99, it's the 99 plus the area to the left and that little tail. And my degrees of freedom of 17, I'll get the same value. I don't normally use this long value. I normally round it to like 4 decimal places. I just wanted to show you what it is for the full value. Okay, so that's how we find that. As usual, we have to meet the requirements for a CI. We want to make sure we're looking at a normal curve. Why use a normal curve if my data is not normal, right? We have a couple different ways, and we already know these ways. If n is greater than or equal to 30, right, that's my central limit theorem. I always look there first. It's like the easy way out. You could just check it, right? And if I ask you, all you can say, well, n's greater than 30, of course, it's normal. Or if we don't have that, then we're going to check our NPP, our normal probability plot on our calculators using our raw data. Okay, so we've done that before. As long as it's fairly linear, we can go ahead and say that it's normal. Okay, here's my interpretations. These interpretations are the same as last class. And now I want to look at using the calculator for the CI. Okay, so to find our CI by hand, we already had the calculation above. And to use our calculator, we're going to go to the same place we did for the proportions. But I notice I have to change my heading here. But for the means, it's test stats, and then I'm going, or stats, then test, and then I'm going to look at T interval. On my calculator, it's option 8, so it's down a little ways, okay? And I have an 84 plus, just so you know. Now here I have two ways to use my input. If I have raw data and I have all these data points listed out and like stored in a list, I would use this option. Or I would use the other option, which is the stats. That means I have summary statistics, like I have X bar and S and N, right? And I'm going to plug all those in. So I just have those listed out here. Okay, so that's how we can use our calculator to find the CI. Let's take a look at this example real quick. So a brand of frozen food dinners is randomly sampled and calories are determined. Our sample size is 40 and our sample mean is 260.5 and our sample standard deviation is 12.1. I want to estimate the population mean. When the word estimate is there, that's how you know you're calculating a CI. And then it continues to say with 95% confidence, so then you can kind of confirm what you were thinking, that it's a CI. Then I want to interpret that value and I want to answer the question. So I'm going to scroll down here to the completed example. So I did it both ways. So I did by hand first. I showed the calculation. It's my X bar plus or minus my T at alpha divided by 2 times my standard error. So I just plugged all my values in and I ended up getting my interval at 256.68 to 264.32. Then I did the same thing with my calculator like we just talked about in the page above, and I got the same answer, which is good. That means I did it right when I did it by hand, okay? You should get the same answer. Now to interpret this value, we are 95% confident that the population mean calories of this brand frozen dinners is between the 256 and the 264. Now my follow-up question, does this CI show that the dinners have 250 calories on average? And I want to know why or why not. So if I ask you something like this, I don't want to say yes or no, I want you to support it. So here the answer is no, and the reason why it's no is because 250 is not inside the CI. So you see here how it says that the dinners have 250, meaning it's equal to 250. If it says something like that, then I'm looking for that number to be inside the CI. Remember, like I mentioned last class, if it's less than or below, then I want my entire CI to be below that value, or greater than or more than. I want my entire CI to be greater than that value or above that value. So in this case, it's no, because 250 is not in the CI. Okay, so I hope that helps. I know that might have been kind of quick, but let me know if you have any questions, and I will actually see you all in a few minutes in the live chat. Thanks.